Hello, friends. Let us imagine that we are sitting together in a quiet evening under a night sky sparkling with countless stars, and I will tell you about the wondrous journey of life in this vast universe. Our Earth, the vibrant blue planet teeming with vitality, is the place where everything unfolds at a dizzying pace, like an endless wheel of survival that never stops turning. Every creature on this planet, from the tiny busy ants scurrying beneath layers of decaying leaves to the powerful predators prowling deep in the forests, is bustling with the daily battle for existence. They compete fiercely for every small morsel of food to sustain their lives, they fight to find mates to preserve their species, they defend their territories to secure safe shelters, and they even vie for their very lives against sudden threats. Can you picture it, the rustling of leaves under the feet of fleeing animals, the scent of damp soil mingled with the metallic tang of blood during chases, and the thrilling tension when everything could end in the blink of an eye? We humans are no exception to this relentless cycle. Our lives are swept into that same unyielding whirl without mercy. We are occupied from dawn until dusk, waking to the shrill ring of alarm clocks, plunging into work filled with endless worries, and juggling countless issues from basic needs like food and shelter to intricate relationships. Time slips away so swiftly that we seldom pause to breathe, to notice the subtle shifts around us, such as the way the sky gradually changes hues at sunset or the whisper of wind through tree canopies. If there is some divine creator who designed life, perhaps they intentionally made it this way, denying us too much time for profound reflection. Just one moment of distraction, and opportunities might vanish forever, or lives could abruptly end in unforeseen accidents. Looking at it overall, life seems perpetually focused on two core objectives: survival and reproduction. For humans, we can elevate these to nobler pursuits, such as building families, chasing careers, or contributing to society, but deep down, the essence remains unchanged, driven by primal instincts that propel us forward. From the instant we let out our first cry at birth, life drags us into that fierce vortex. If we calculate the time in precise detail, you will see that most of our lifespan is devoted to sleep for energy recovery and to earning a living for food, housing, and security. We truly have little room left to ponder matters farther afield, like the meaning of the universe or our own place within it. Yet sometimes, just sometimes, on those silent late nights when the chirping of insects echoes outside the window, we gaze up at the star-filled night sky, twinkling like diamonds scattered across black velvet, and wonder, what purpose do those stars serve? Do they connect to us in any way, or are they merely distant, cold specks of light? Let me take you closer to the Milky Way, our cosmic home, a colossal city of stars with a diameter of at least 100,000 light-years, and even up to 180,000 light-years according to the latest estimates from the Gaia mission of the European Space Agency. Its population ranges from 100 billion to 400 billion stars, with recent figures leaning toward approximately 250 billion observable stars. Try to envision it, a number so immense that our brains struggle to comprehend, like standing in a midnight desert gazing at endless grains of glowing sand. Observations from the Hubble Space Telescope, the James Webb Space Telescope, and data updated through the year 2025 reveal that every 100 years, the Milky Way loses between 1 and 2 stars through violent supernova explosions, with bursts of energy echoing through the frigid void of space. In exchange, during the same period, it welcomes between 300 and 600 new stars into existence, and according to fresh studies from the ALMA telescope and Gaia, the formation rate for Sun-like stars stands at about 1.9 per year, while the total reaches from 3 to 6 new stars annually when including the majority of low-mass red dwarfs with approximately 0.5 times the Sun's mass. This imbalance makes the universe ever more crowded, even though the peak era of star formation passed long ago, billions of years in the past. These figures are quite reliable, drawn from gamma-ray observations of supernovae and infrared emissions from star-forming regions, though variations persist depending on computational models. Recent advancements in 2025, including Gaia's final data release before its mission concluded in March, have refined these rates further, showing that the Milky Way's star formation efficiency in dense molecular clouds is higher than previously thought. contributing to about 1 solar mass of new stars per year overall. Expanding to the entire observable universe, estimated at around 2 trillion galaxies from Hubble and James Webb updates in 2025, each passing second witnesses between 30 and 130 stars concluding their lives in supernova blasts, unleashing radiant energy like a resounding farewell. Conversely, every second sees between 3,000 and 4,800 new stars igniting from cold clouds of gas and dust. These numbers stem from major sky survey projects like the Sloan Digital Sky Survey and modern telescopes, detected through high-energy gamma rays from supernovae, ultraviolet light from newly born massive stars, and infrared from smaller ones. A single second is fleeting for us, gone between a blink, but in the cosmos, it holds immense significance, driving constant change in the grand tapestry. The James Webb Space Telescope's deep-field observations in 2025 have pushed the estimate of galaxies even higher, suggesting up to 2,500 billion, as fainter, more distant ones come into view, reshaping our understanding of cosmic evolution. Imagine a massive star, super heavy, super hot, and super bright, a gigantic sphere of plasma hovering in the dark expanse, emitting dazzling light that warms distant planets. Through observations from NASA's Fermi Telescope or Europe's Integral, such a star explodes in a supernova in mere seconds to minutes, or a neutron star triggers a thermonuclear burst in just 1 to 2 seconds. In that instant, the released energy surpasses the total it emitted over its lifetime via ordinary photons, like a thunderous boom shattering the universe's silence. After the blast, only the core remains, with a mass of about 10 to 20% of the original, meaning nearly all matter is ejected as scorching gas, forming stunning nebulae clouds. The energy conversion accounts for roughly 1% of the mass, per Einstein's equation E equals mc squared, yet it is enough to illuminate an entire galaxy for a moment. These explosions not only recycle elements but also trigger subsequent star formation in nearby clouds, as the shockwaves compress gas, accelerating the birth of new stellar generations. The ejected matter drifts through space, mingling with cosmic dust under chaotic yet precise physical laws. Remnants often glow for weeks to months due to the decay of heavy elements like iron, nickel, and cobalt, casting an ethereal light like will-o'-the-wisps. Some exceptional cases endure for thousands or even millions of years, such as the Crab Nebula, located 6,500 light-years from Earth, the remnant of an explosion in the year 1054 according to ancient Chinese records, not 1945 before the Common Era as sometimes misstated. At its heart is a pulsar spinning 30 times per second, emitting radiation from radio waves to gamma rays via the synchrotron mechanism, with a powerful magnetic field sweeping charged particles. It will continue shining for several tens of thousands of years more, like an unwavering cosmic lighthouse flashing eternally. Recent 2025 spectral analyses from the James Webb Space Telescope have revealed intricate details in the crab's filaments, showing layers of ionized gas enriched with silicon and sulfur, providing clues to the supernova's progenitor star. Thanks to modern technology like the James Webb Space Telescope, we behold hundreds of nebulae within the Milky Way, each a scar from a ferocious explosion, with unique shapes like human fingerprints, no two entirely alike. Just as in life, where each species has its distinct form, and even individuals within a species differ subtly. Is this mere random chaos, or does a deeper order underlie it? To bring the story to life more vividly, allow me to recount the tale of Bender, the cosmic bartender, a character I have imagined to illustrate the journey of creating life. Our bodies consist of 65% oxygen, 18.5% carbon, 9.5% hydrogen, 3.2% nitrogen, 1.5% calcium, 1% phosphorus, and the remainder as trace elements. By compound, it is mostly water, organic molecules, and bone structure. Bender works at the universe's bar, tasked with mixing the life cocktail using every element from the periodic table, adjusting temperatures and pressures over 13 billion years, but he must build his lab from hydrogen alone, aided by the 4 fundamental forces and 3 helpful packages. Initially bewildered, he opens the first package, Instructions for star forging. Gather hydrogen, stir thoroughly, let gravity handle the rest, and stars are born, radiating heat and brilliant light. Massive stars explode, forging new elements from the debris. He crafts more stars, turning the universe into a forge with galaxies as hundreds of billions of furnaces. After 1 billion years, he collects materials, tries billions of mixtures, but all fail. He opens the second package. Patience is key, find the right locale with moderate temperatures. He tweaks cooler small stars to form diverse planets with varied environments, adding lightning and rain, harnessing the four forces. He waits millions of years to check, but life eludes him still. Time passes, and desperation grows for success. He opens the third package. The universe is already the perfect cocktail, and life is woven into its history. He steps out, awestruck by the swirling, glittering galaxy, pours a few drops of the cocktail into Earth's oceans, keeps the secret, and realizes that life harbors soul, intelligence, and an endless flow of energy. In the year 1953, the Miller-Urey experiment simulated primordial Earth with ammonia, methane, water vapor, and hydrogen, zapping them with electricity like lightning, yielding over 20 amino acids and pre-proteins, with 10% organic yield. In the year 2024, modern versions incorporated lasers and ultraviolet light, producing adenine and sugars, the building blocks of nucleotides. In the year 1980, hydrothermal vent experiments with iron, sulfur, and nickel at temperatures of 100 to 400 degrees Celsius created lipids and peptids. From 2020 to the present, NASA has employed artificial intelligence to simulate comets and Europa's subsurface, suggesting life from organic phosphorus molecules. Despite numerous experiments, we still do not know exactly how life began, but 2025 studies from the James Webb Space Telescope have detected complex molecules in star-forming clouds, bolstering panspermia theories from cosmic origins. A groundbreaking Harvard experiment in July 2025 used synthetic self-assembling materials to mimic protocell formation, showing how lipid membranes could encapsulate RNA precursors under early Earth conditions, bridging the gap from chemistry to biology. Additionally, a March 2025 update to the Miller-Urey setup incorporated microlightning in water droplets, enhancing amino acid yields by 50% and revealing pathways for peptide bonding without enzymes. Returning to Bender, after billions of years of waiting, he realizes life is intrinsic to the universe. He pours the cocktail, savors it, understanding that the mixing is not mere chaos but infused with soul. In natural disasters, earthquakes and tsunamis are terrifying, but storms cause the most widespread damage through flooding and landslides. The strongest, Patricia in the year 2015, with winds of 345 km per hour in the eastern Pacific, made landfall in Mexico. Second was Haiyan in 2013, at 315 km per hour in the Philippines. Following were Goni in 2020, Ida in 1958, and Tip in 1979, all exceeding 300 km per hour in the western Pacific, striking East Asia and Southeast Asia like Japan and the Philippines. Vietnam also suffers from this geographic injustice. But storms have positive sides, regulating climate. Tropical storms form near the equator from 23.5 degrees north to south, where it is hottest and spins fastest. Temperate storms arise from 30 to 60 degrees, clashing cold and warm air. Each year, 80 to 90 tropical storms occur, with 60% reaching over 120 km per hour. Temperate storms number in the thousands but are weaker. All originate over oceans, powered by thermodynamics, Coriolis effect, and Bernoulli's principle. The sun provides heat, with Earth receiving 1,360 watts per square meter at the top of the atmosphere, absorbing an average of 240 watts per square meter. Cooling happens via evaporation, convection, and radiation, birthing storms as a byproduct. Tropics receive 60 to 70% of radiation despite covering 40% of the area, with the Pacific accounting for half the ocean surface. The atmosphere spans 100 kilometers thick, with temperature differences from poles to equator, oceans covering 70% of the surface, and Coriolis force creating counterclockwise swirls in the north and clockwise in the south. The equator lacks storms because winds disrupt convection. Sea temperatures of 26.5 degrees Celsius sustain storm initiation for 48 hours, while 28 to 30 degrees fuel stronger ones. Evaporation carries heat and moisture upward, forming low pressure that draws in air, twisted by Coriolis. Water vapor condenses into spiral clouds. Low pressure boosts evaporation despite blocking sunlight. Storms dissipate via wind shear from differing directions at heights, sudden cold air intrusions, high pressure overhead, or land friction, dissolving in 48 hours. The idea of nuclear bombing storms arose in the 1950s and 60s in the United States, but radiation hazards outweighed benefits. Storms balance heat, preventing desertification or polar ice expansion. In 2025, the Atlantic season saw Hurricane Melissa as the strongest yet, with winds peaking at 260 km per hour and a pressure of 892 hectopascals, causing record flooding in the southeastern United States, while in the Pacific, Super Typhoon Ragasa reached Category 5 with 270 km per hour winds, devastating parts of the Philippines and underscoring climate change's role in intensifying storms. Bernoulli's principle states that faster velocity lowers pressure. Winds skimming roofs create low pressure outside, sucking inward, while high pressure inside pushes out. Winds at 100 km per hour suck with 463 newtons per square meter, or 47 kilograms per square meter. At 200 km per hour, it is 1,852 newtons per square meter, or 190 kilograms. At 300 km per hour, 4,167 newtons per square meter, or 420 kilograms. For a 50 square meter roof, this multiplies to tons of force. Light metal roofs lift easily. Remedies include securing firmly, placing sandbags or bricks to add weight and disrupt airflow, weakening Bernoulli's effect. The Nobel Prize is the most prestigious award, valued over $1 million, symbolizing intellect and perseverance. The Physics Nobel is the toughest, demanding deep mathematics and extraordinary thinking. Peace is humanistic yet controversial. In 2025, the Nobel Prize in Physics went to John Clark, Michel Deverett, and John Martinis for discovering macroscopic quantum tunneling and quantizing energy in electrical circuits, using Josephson superconducting junctions to prove macroscopic tunneling, foundational for quantum computing. Building on the Bardeen-Cooper-Schrieffer theory of the year 1957, which explained superconductivity via zero-spin Cooper pairs acting as bosons sliding without collision, Josephson in 1962 predicted supercurrents tunneling barriers, earning the Nobel in 1973. Leggett predicted macroscopic tunneling. Experiments in 1985 confirmed synchronized electron tunneling ratios. It was awarded late due to caution, needing clear proof. This extends macroscopic quantum effects at ultra-low temperatures, underpinning quantum computers. Clark, born in 1936 in Australia, pioneered superconducting quantum interference devices for sensitive measurements. Deverett, born 1953 in France, advanced circuit quantum electrodynamics. Martinis, born 1953 in the United States, integrated these for scalable qubits. Their work, spanning decades, has accelerated quantum tech, with applications in secure communication and drug discovery by 2025. Conversations among leaders of Russia, North Korea, and China on replacing organs to live to 150 years ignite the immortal longing from Qin Shi Huang to alchemists. Longevity extension via genes, cells, or freezing. Death stems from DNA replication errors, accumulation, or evolution favoring generational replacement. Cells replicate about 50 times per Hayflick limit, with telomeres shortening progressively. The enzyme telomerase rebuilds them, earning the Nobel in 2009 for Blackburn, Grader, and Sostek. But unlimited rebuilding risks cancer, as 85 to 90% of cancer cells hijack telomerase, or 10 to 15% self-replicate telomers. Telomerase inhibitors, targeted vaccines, or telomere destruction drugs are in development. Stem cells offer perfect replacements from bone marrow, fat, blood, brain, or umbilical cords. Yamanaka's 4 genes, OSKM, in 2006 reset cells to embryonic states, winning the Nobel in 2012. Partial reprogramming rejuvenates partially, extending mouse lifespan by 20 to 31% without cancer. Human trials began in 2023, with OSK gene therapy in 2024 prolonging old mice's lives. By 2025, OpenAI collaborations with Retro Biosciences produced enhanced Yamanaka variants, like redesigned SOX2 and KLF4 using AI models, boosting rejuvenation efficiency by 40% in lab cells without full pluripotency risks. Clinical trials for partial reprogramming in age-related macular degeneration advanced to Phase 2, showing vision improvements in elderly participants. Enzymes clear senescent cell debris and inflammation. Cryonics differs from hibernation, replacing blood with anticoagulants before freezing at -196 degrees Celsius in liquid nitrogen. About 500 people are preserved, 4,000 registered, with companies like Tomorrow Bio expanding from Europe to the United States in 2025. Hopes for future revival persist, though currently unfeasible, but science advances rapidly, who knows what tomorrow brings. Emerging neural preservation techniques in 2025, using vitrification to avoid ice crystals, have improved brain tissue integrity post-thaw in animal models, fueling optimism for whole-body revival. You see, friends, from cosmic stars to tiny cells, everything connects in a wondrous, emotional chaos that is profoundly beautiful. We are part of that grand canvas. Let us cherish every moment. Until we meet again.